DC motors can be made with different windings. This third chapter deals with the properties of the different windings for one motor type. In the Maxon catalog, the different windings of a motor type are listed in columns. The resistance increases from left to right. The first winding on the left is made with a wire of a large diameter, so only a few winding terms can be placed in the air gap between housing and permanent magnet. Correspondingly, the resistance is low and the current needed high, however, at a low voltage. In some cases, the terminal resistance is even dominated by the brush resistance. The last winding on the right is made with the thinnest wires and with many turns. The resistance is more important and the needed voltages are high, but the current flow, on the other hand, is rather low. How does the motor limits change over the winding series? It looks like the maximum speed remains the same for all the different windings. And also the nominal torque, it is the border of the continuous operating range, is almost identical for all the windings. How does the speed-torque line change over the winding series? Again, speed-torque gradient is almost identical. Each winding has its particular nominal voltage, and this is selected to give a similar no-load speed for all the windings. Accordingly, the stall torque and nominal speed are very similar too. Here's a graphical representation of the findings of the previous slide. The nominal torque has slight changes in the border of the continuous operating range. The speed-torque lines lie in a very narrow band. Essentially, this is how the nominal voltages are assigned to the different windings. What we can learn from this is that for a given motor type, the mechanical behavior and the limits are essentially identical. It doesn't matter which winding you take. It also means that load operating points can equally well be reached with any of these windings. What changes over the different windings is voltage and current. We have already seen that the nominal voltage increases with increasing winding resistance. It is from left to right. All the different current parameters are highest for the low resistance windings. This means for the same torque to be produced, a high resistance winding needs less current. At the end, the same mechanical output power, speed and torque, can be obtained with a low resistance winding with a low voltage and high current, or with a high resistance winding at a higher voltage but at a lower current. This means that the same mechanical output can be reached with any winding but with different electrical input voltage and current. The increasing voltage is compensated by a decreasing speed constant, resulting in the same output speed. The same output torque can be reached with all the winding with less and less current, because this is compensated by a higher and higher torque constant. Here's again a graphical representation of the findings of the previous slide. Let's come from the application point of view, where the available voltage is usually fixed. Selecting the winding with nominal voltage similar to the available voltage may not be the right choice. Here, for example, the acceleration cannot be fully achieved when selecting the winding with 24-volt nominal voltage. The winding to the left with a higher speed constant, nominal voltage of 18 volt, covers all the operation points easily. A speed or position controller will adjust the motor voltage to the lower values needed. However, the current requirements are higher. The winding with even lower nominal voltage of 12 volt won't make use of the available voltage. The controller has to reduce the motor voltage to about 12 volt, but the current needed is even higher. The two other windings with higher nominal voltages cannot reach the required speed because the speed constant is too low. Here's the summary of Chapter 3. What you have learned is that all windings of a motor type can produce the same mechanical output. It is the same speed and torque. However, from left to right, the windings need more voltage, but less current. The goal is to select the winding that fits best your power supply.